In this lecture, we will discuss about Biot Savart Law and Prandtl's lifting line theory. Let us look at the theoretical model of flow past a finite wing. The first theoretical model for flow past a finite wing was proposed by Ludwig Prandtl. And he proposed it through the classical lifting line theory. So, what was the motivation behind the theory? The motivation was to model the finite wing using a horseshoe vortex. So, what is it comprised of? It is comprised of a bound vortex portion which runs along the span of the wing and a pair of free trailing vortices which are attached at the two ends of the bound vortex and stretching infinitely into the wake of the wing. So, here is your finite wing, this is your span, this is your chord. Let us say you have a rectangular planform. So, when there is a flow past this wing, the effect of that flow was modeled by Ludwig Prandtl by using a horseshoe vortex. Which would look more like this in the context of the wing, but it is just represented in the form of a horseshoe vortex which is present in a uniform flow field, and that vortex comprises of a portion which is along the span of the wing, which is called as the bound vortex, and a pair of trailing vortices. These are the two trailing vortices forming a pair which stretches to infinity. So, we will discuss more on this in the subsequent slides. So, the total vortex structure is called as a horseshoe vortex. Why is it called that way? It is called that way because of its resemblance with the shape of a horseshoe. So, this horseshoe vortex induces a velocity field in its neighborhood, which is a fair approximation of the downwash that we observe around a finite wing. So, Prandtl realized that with a single horseshoe vortex, the approximation was not all that satisfactory. Therefore, instead of using just one such horseshoe vortex, he used innumerable of them. So, therefore, he proposed a lifting line at the location of the bound vortex, along which he superposed infinite number of horseshoe vortices of infinite simul strength. This gave a very good approximation of the real flow field, and the circulation distribution along the wingspan was also modeled. So, this is the background of the classical lifting line theory proposed by Ludwig Prandtl. So, some of the things that we just introduced here through a few terminologies and concepts will be elaborated further. So, let us move on. So, before we discuss about the lifting line theory, we need to develop some tools, and those tools come from the concept of the so called vortex filament and the accompanying Biot Savart law. So, let us try to recall what a vortex filament is. Earlier, we were looking at a vortex sheet. So, when we were discussing about the thin airfoil theory, we first discussed that we can have a distribution of vorticity along the camber line, and then we simplified it further and we said that it can be distributed along the chord line. So, there were innumerable number of discrete vortices which practically formed a sheet. Now, if you were looking into the plane of this page, then you would see each one of those vortices moving in the depth direction with a particular value of vorticity. So, these could then be considered as vortex filaments, which are stretching along the depth direction. So, we have drawn such a vortex filament, but which could be arbitrarily curved and has a strength gamma. Now, the Biot Savart law was originally proposed in the area of electromagnetism, and the idea was that a relation was developed which looks like this. And looks so very similar to the form that we are using here. So, in the context of electromagnetism, B was the magnetic field strength, that is, and I was the electric current, and mu was the permeability of the medium. So, this law basically gave a relation between the current that was carried by a conductor of elemental length d l that was inducing a magnetic field at a point which was expressed through the vector r, that was the distance from the dl element carrying the current and the point at which we were looking at the magnetic field induced by that current. So, that was the Biot Savart law developed in the area of electromagnetism, which has now been extended to aerodynamics, where we are looking at a vortex filament inducing a velocity in the flow field, and they work in both domains because they broadly belong to potential fields. Whether it is electromagnetism or it is a potential flow field, they work in a very similar or analogous manner. So, based on that, the Biot Savart law in aerodynamics looks like this, where this is the velocity induced in the flow field at a particular field point. It is induced by a vortex filament of strength gamma in terms of the circulation strength. This is the elemental length of the vortex filament. This is the position vector of the point with respect to that element, and of course, this is the distance cubed. So, that is the relation. So, if you look at the geometry of the problem, this is how it works out. This is the vortex filament, the curve. This is the strength of that vortex filament. This is that small element located along the vortex element. This is the position vector of the point P at which the velocity is being induced. Now, from the cross product you can work out very easily that the velocity will be induced downwards. So, that is all about the Biot Savart law. Now, instead of a curved filament, if you assume that it is a straight vortex filament and it is infinitely long. So, it stretches from negative to positive infinity. So, in such a case, if you integrate the effect of elemental lengths of the vortex filament and try to find out the integrated effect on a field point, there will be a sum total velocity which will be induced in the negative z direction, and that is given by this expression. So, that is the velocity induced at a point P by an infinite straight vortex filament. I leave it to you to explore how you can arrive at this relation by integrating the Biot Savart law over such an infinitely stretched straight vortex filament. So, take it as a homework. Similarly, we can deal with a semi-infinite straight vortex filament, and in that case it does not stretch to negative infinity, but stretches from the origin to positive infinity, and then it is again the integrated effect of the vorticity that is lying along that vortex filament, and the integrated effect comes out to be this. So, it is again pointing towards the negative z direction. So, this is the axis system that we have marked here, and that is how it works out. Again try to work this relation out from the Biot Savart law. So, these two relations that we worked out are going to be very useful for us. We will use them in due course. We look at a very important theorem which we call as Helmholtz theorem, and there are two parts to this theorem. The first part says that the strength of a vortex filament is constant along its length. So, we just looked at a vortex filament, and we need to know that the strength of that vortex filament is invariant along its length. The second part of the theorem says that a vortex filament cannot end in a fluid. So, it cannot just have finite ends like this. It must extend to the boundaries of the fluid, which can be at plus or minus infinity or form a closed path. Okay, so, it can also form closed paths like this, else it can extend to infinity, like we looked at the horseshoe vortex for example, but it cannot abruptly end somewhere in the domain. So, we have to keep the statements of this theorem in mind as we move on. So, most finite wings have a variable chord, with the exception of a simple rectangular wing. We had discussed it in the previous lecture. We could have, for example, a tapered wing. If a wing has the same airfoil section along the span, but with different chord length, then the wing is said to be geometrically twisted. For such wings, alpha is different at different span-wise locations. Here we need to say that along the span, if it has different chord length, then it also has the tapering effect. And then the geometric twist comes when the alpha is different at different span-wise locations. So, geometric twisting is to be associated with the alpha changing at different span-wise locations, and having different chord length is associated with the tapering of the wing. If the tip is at a lower angle of attack than the root, the wing is said to have a washout. So, tip has a lower alpha. So, that is a washout, which basically means if you look at the cross section of the wing near the root, if it is a tapered wing, the chord length will be larger, and at the tip the chord length will be smaller and the alpha will be lesser. So, it may be like this, or you could also show it in another way like this. If the tip is at a higher alpha than the root, the wing has wash in. So, when does that happen? You have lower at the root and higher at the tip. So, that gives a wash in. If a wing has different airfoil sections along the span with different values of 0 lift angle of attack, this is called as an aerodynamic twist. So, under the above conditions, lift becomes a function of the span-wise location in general. Lift distribution should go to 0 at the tips, because you cannot have a pressure imbalance at the tips. You do not have a solid surface, the solid surface which is sustaining the lift and the pressure difference which causes the lift, that ends there, and therefore, there has to be pressure equalization and therefore, lift going to 0 there. So, the pressure equalization enforces this condition, that the bottom and the top parts of the wing must have the same pressure. So, the lift distribution may look somewhat like this, where this is the mid span location, where the lift is highest per unit span, and then as you move towards the ends minus b by 2 to plus b by 2, the ends have 0 lift. They also have 0 delta p, which is actually leading to this 0 lift. So, in more like an isometric view, you can look at it this way. So, we have drawn a typical rectangular planform, and on that we have tried drawing it at the mid chord location, that how lift can vary along the span wise direction of the wing. Let us look at the horseshoe vortex once again, and let us look at it from the perspective of the finite wing. So, there is a uniform flow impinging on a finite wing of span b, and the mid span location corresponds to y equal to 0, and then the approximation that is being proposed, which was actually proposed by Prandtl, was that a horseshoe vortex will simulate the effect of the wing. So, how does the horseshoe vortex look? It looks like the shape that we explained earlier also, that it has a bound vortex, which is a straight part of the vortex which spans the wing, and then there are 2 free trailing vortices. And of course, the strength of the vortex filament does not change along the length, and it stretches to infinity through the free trailing vortices. So, they satisfy Helmholtz theorem's requirements. Now, it was found by Prandtl that this does not necessarily give you a very favorable distribution of the induced velocities in the field. So, let us try to derive a relation which tries to prove that point. So, what Prandtl found out was that the downwash at any field point due to the trailing part of the vortices would be given by a relation like this. So, if you take any point, let us say y on the bound vortex, and you try to find out what is the induced W at that point. Remember that the bound vortex by itself does not induce anything at that point y, it is only induced by these 2 sections of the trailing vortices. So, this distance is b by 2 plus y, and the other distance is b by 2 minus y, which you can see over here in the denominator. And remember that we are basically using the expression minus gamma by 4 pi h over here, because these are semi infinite vortex filaments. So, they begin here and they stretch up to infinity. So, if you simplify this expression, what you get is minus gamma by 4 pi into b by 2 square minus y square. Now, as a consequence of this, what happens is, let us try to see a plot which will show us how the distribution of the W component of velocity, which is basically the downwash, looks like with that single horseshoe vortex. So, the downwash distribution looks somewhat like this, and remember that here it is predicting infinite downwash, which is kind of consistent, which is kind of inconsistent with what we see in reality. There can never be infinite downwash at the edges or the tips of the wing. So, this is not a very realistic representation of the wing anyway. So, Prandtl and his team was very perplexed for years before they could resolve this problem, and they could understand that this has to be resolved by having a more pragmatic approach to solving the problem. And what they proposed was, they proposed that let there be multiple horseshoe vortices instead of just 1. So, what effect does that have? Let us try to see. So, let this be y equal to 0 and let the most outer pair of trailing vortices contribute a little bit of circulation d gamma 3. Then the next inner one, let that contribute d gamma 2, and the innermost one, let that contribute d gamma 1. So, in that case what is happening is that the circulation is gradually growing up as we move inwards away from the tips towards the mid span location, because each one of them contribute to build up the total circulation. So, in the mid span location what is happening is that you have a sum total effect So, at the mid span location they sum up their effects, that is one. The other thing is that whenever there is a change in the circulation along the lifting line, an equivalent amount of vorticity moves down into the wake of the wing. So, there is an equivalent amount of trailing vortex which is shed into the wake. They further refined the model subsequently and made it look like a continuous sheet of vorticity instead of having discrete elemental vorticities. They made it a continuous sheet, and that would mean that instead of having stepwise changes in the circulation that is there in the lifting line in the form of the bound vortex, you will basically have a continuous change of the gamma. So, this is your trailing vortex sheet. And obviously, when you have such a continuous sheet, the gamma that builds up is very, very uniform. So, let us say this is the gamma at the mid span. You can figure out that that will be the maximum value. Let us call that as gamma 0, that is the maximum value. Let us mark the ends as minus b by 2 and b by 2. So, this is the uniform flow which is approaching from upstream, and let us identify a location, say y. So, this is at a distance y and a small element around that y of width dy, let us say this is dy. Let us mark another point, let us call it y naught, where y naught is greater than y here, at least as we have drawn it in this figure. Then let us identify a small element on the trailing vortex at the y location. Let this be dx. Let us call this angle that is subtended by the line joining that dx element with y naught as theta, and the vector which connects that elemental length with u naught, we will call it as r. What is the distance between the y to y naught point? That we will mark as, say, you can call it as h, for example. Okay. So, this is the h. Remember that this is a trailing vortex which has this sense of rotation and it carries a strength d gamma. Now, by applying the concept that per unit length, this is the rate at which the gamma distribution along the lifting line is changing, we indicate it as d gamma dy. Over a length dy, it will change by this amount. So, that small element that we have marked here, over that length, this is the change in gamma, and that must be the gamma that is being shed into the wake. So, the velocity that this d gamma will induce at the field point y naught, we will mark it as d w and we will express it this way, d gamma dy into dy. Notice that we have put a negative sign there, we will try to justify that, 4 pi y naught minus y, which we called as h. So, we are basically using this equation that we had mentioned before. Does it work appropriately? Keep in mind the direction of the trailing vortex. Remember that these are all moving in a clockwise sense, if we look at them, while the others are moving in counterclockwise sense. That is just about y equal to 0, there is a change in the direction. Now, if you notice carefully, this particular nature of the vortex, it will end up inducing an upwash at the point y naught, because that point y naught is lying to the right of this counterclockwise moving vortex. If it was lying to the left of this counterclockwise vortex, then it would have faced upwash. So, y naught minus y is positive, d gamma dy happens to be a negative term, because if you look at this change of gamma over the dy distance, there has been a drop in the gamma, it is reducing because you are moving away from the maximum point anyway. Therefore, d gamma dy is a negative term, this is a positive term, which means that this will end up giving you a positive w value. That means the upwash that we were talking about, which is consistently modeled here using this equation. What if y naught minus y was less than 0? That means y naught was less than y to the left of y. In that case, this would have become positive and then it will work as a downwash. Rather, I should put it this way, that in that case y naught minus y would become negative, I am sorry, and this remains negative. Therefore, the dw will have a negative sign and thereby there would be a downwash. So, this is a consistent representation, that is what we have come to know. So, we are moving towards a model where the downwash distribution will be more appropriately modeled, and it will be appropriately modeled through a continuous distribution of vorticity, trailing vorticity in the wake of the wing, and thereby there would be a gradual change in the gamma value along the lifting line. That means, the bound vortex strength will change as a function of y. So, With that, we come to the end of this lecture. We will continue with the Prandtl lifting line theory in the subsequent lecture. Thank you.